Picture this. You tap a web address into your browser, any address at all, and bam, the page just pops up. It feels almost like magic, doesn't it?
It really does. But what's fascinating here is the incredibly efficient system working behind the scenes, making that digital leap happen in, well, a blink.
And at the very heart of it is DNS, the domain name system.
That's the one.
Exactly. And that's precisely what we're diving into today. We've taken a really deep look at a glossary of DNS terms, a detailed breakdown of how DNS actually works.
They also explore the different kinds of companies involved, the service providers.
Right. So our mission for you listening is to demystify this kind of invisible infrastructure that's essential for, well, pretty much everything you do online.
We want you to understand not just the basics, but, why it's so fundamental.
Yeah, to see it not just as a technical term, but as this core system. And hopefully leave you feeling informed, maybe even a bit amazed by it all.
Connecting it to the bigger picture, DNS is really one of those unsung heroes of the internet. It's the bedrock allowing us to just navigate so easily.
Okay, let's get into the core of it then. We keep hearing domain names and IP addresses. What's the basic difference there?
So think of it like this. A domain name, google.com, that's the easy, human-friendly name we remember and type.
Okay.
An IP address, something like, 142.250.190.78. That's the actual numerical address computers use to find each other on the network.
So google.com is the name, 142 dot whatever is the digital street address.
Precisely, like the name of a business versus its precise location on a map.
Gotcha. And the process of turning that name into the number.
That's called DNS resolution. It's basically the internet doing a quick lookup.
Like flipping through that giant internet phone book? Okay.
Exactly.
Now, we also see terms like DNS cache and TTL. What are those about?
Right. So imagine you look up a friend's address. You probably don't look it up every single time you visit, right?
No, I'd remember it after the first time.
Exactly. You remember it for a while. That's sort of like DNS cache. Your computer or the DNS server you're using, it temporarily stores the IP addresses of websites you've recently visited.
Okay. So it speeds things up.
Massively.
Yeah.
Because it doesn't have to do the whole lookup process from scratch every single time.
So it's like my browser having a little memory bank for addresses. And TTL, what's that?
TTL stands for time to live. And it's basically the expiration date on that stored information.
Expiration date.
Yeah, it tells your computer or the server how long it's allowed to remember that IP address before it absolutely has to check for an update.
Okay, that makes sense. Because website addresses can change, right?
Exactly. You wouldn't want your computer holding on to old, outdated directions. TTL prevents that.
Got it. Need that expiry so the device knows when to double check. Okay, and then there's DNS propagation. That sounds like spreading out.
You've got it. When someone makes a change to a website's DNS records, say, they move the site to a new server with a new IP address.
Right.
Those changes don't just instantly appear everywhere across the globe. DNS propagation is the time it takes for those updates to spread and get reflected on all the various DNS servers worldwide.
So like news traveling. Takes a while for everyone to get the memo.
That's a great analogy. It takes time for everyone to get the latest information, so there might be a short period where some people get the new address and others still get the old one.
Right. So if a website changes its digital address, it might take, minutes, hours before my computer knows the new spot.
It can vary, yeah. Sometimes quick, sometimes longer.
Okay, we've got the basic building blocks. Domain name, IP address, lookup, cache, TTL propagation.
Yeah.
Now, how does this whole DNS resolution thing actually work, like step by step?
Okay, it's a pretty cool sequence, actually. Let's say you type example.com into your browser.
Yeah.
The very first thing your computer does is check its own local DNS cache, your browser cache, your OS cache.
To see if it already knows the address from before.
Exactly. If it finds the IP address stored there and the TTL hasn't expired, boom, done. It connects directly.
Nice and efficient. Love that. But what if it's a new site?
Yeah.
Or the cache is empty, or the TTL is expired?
That's when the real detective work begins. Your computer sends a query out. Usually it goes to the DNS server provided by your internet service provider, your ISP.
Okay.
This server is known as a recursive resolver. Think of it as your personal investigator. Its whole job is to hunt down the answer for you.
So my computer asks my ISP server, hey, what's the IP for example.com? And if that server doesn't know or doesn't have it cached.
Good question. If the recursive resolver doesn't have the answer cached either, it starts querying a hierarchy of other, more specialized DNS servers.
A hierarchy, okay.
First stop, A root server. There are only a handful of these clusters globally, managing the very top of the DNS tree.
Root server, like the starting point.
Exactly. The root server doesn't know the specific IP, for example, .com, but it knows who manages the .com part. It says, I don't know, but go talk to the .com TLD server.
TLD, top-level domain, like .com, .org, .net.
You got it. So the root server directs the recursive resolver to the appropriate TLD server. The TLD server manages all the domains ending in its specific suffix, like knowing the right neighborhood.
Okay, so the root points to the neighborhood. The TLD server knows the streets in that neighborhood. What's next?
The TLD server looks at example.com and says, for example, you need to talk to these specific servers. It points the recursive resolver to the authoritative name servers for the example.com domain.
Authoritative. That sounds definitive.
It is. The authoritative server is the ultimate source of truth. It holds the actual official DNS records for that specific domain, including its A record, which has the IP address. It's like finally finding the homeowner who knows their exact address.
Got it. So root points to TLD, TLD points to authoritative, authoritative gives the answer to the IP address.
Exactly. The authoritative server sends the IP address back to the recursive resolver,
Which is my ISP's server, the detective.
Right. The recursive resolver then sends that IP address back to your computer. And now your computer can finally make the connection directly to the website's server using that IP address and load the page.
Wow. That's quite a journey for just typing in a web address.
It is. And one crucial last step. The recursive resolver also caches that answer the IP address for example.com, remembering it for the duration specified by the TTL.
So the next time someone on my same ISP network asks for example.com, the resolver might already have it.
Precisely. Makes the whole system much faster for subsequent requests. It's this layered caching and querying that makes it work so efficiently at scale.
That whole sequence, asking different levels. It really is like asking for directions. Start broad, get specific. Very cool.
It's a robust system. Okay, so we mentioned these different server types. Maybe we should dive a little deeper into those roles.
Yeah, good idea. Our sources broke them down. We have the recursive resolver or internet detective. Let's talk about the root server again. What's its key role?
The root servers are, well, fundamental. They sit at the absolute top of the hierarchy. They don't hold info about specific domains like example.com, but they know where to send you next which TLD server to ask. They are the initial guides. Managed by various organizations globally, absolutely critical.
The starting point for almost every lookup that isn't cached.
Okay.
And the TLD servers. We said .com, .org.
Exactly. They manage the next level down. The .com TLD server knows the authoritative servers for all the .com domains. The .org TLD server knows the authoritative servers for all the .org domains, and so on. They know who's in charge for each domain within their top-level zone.
Right. And the authoritative server, that's the final stop, the one with the actual records.
Precisely. That's the server that holds the definitive DNS records, the A record, MX records, all that stuff for a specific domain. The domain owner controls the records on their authoritative name servers. If you move your website, you update the records here.
Okay. And there was one more type mentioned. A forwarding server. What does that do?
Yeah. A forwarding server is a bit different. It's a DNS server that doesn't usually try to resolve queries itself through that whole root TLD authoritative process.
What does it do?
It just passes the request, forwards it to another DNS server. Often, this might be the ISP's recursive resolver, or maybe a public DNS service like Google's or Cloudflare's.
Why would you use that?
Oh, various reasons. Sometimes in corporate networks for specific routing, maybe for centralized caching within a local network, or to enforce certain policies. Think of it like a receptionist directing a call to the right department instead of answering the query themselves.
Interesting. Okay, so different servers, distinct roles, all working together. Now, our sources also went into the different types of DNS records. These sound like the actual pieces of info stored on those authoritative servers.
That's exactly right. These records are the actual data nuggets in the DNS. The most common, the most basic is the A record.
A record. A4?
Address. An A record maps a domain name directly to an IPv4 address. That's the standard 32-bit IP address format we're mostly used to seeing, like the 142.x.x.x example earlier.
Okay, the standard one. And then there's AAA, quad A.
The AAA record does the same thing, maps a domain to an address, but it points to an IPv6 address.
IPv6.
But
this is the newer, much longer one.
Exactly. IPv6 uses 128 bits, gives us vastly more addresses. We're kind of running out of IPv4, so IPv6 is the future. AAA records handle that mapping. So A and AAA are the core where's this website records.
Got it. Basic address labels, one for now, one for the future. What about CNAME records? That sounds like nickname.
That's a perfect way to think about it. CNAME stands for canonical name. It essentially creates an alias. It points one domain name to another domain name, not directly to an IP address.
Example.
Sure. A common one is having www.example.com be a CNAME record pointing to example.com. So if the IP address for example.com changes, you only need to update the A record for example.com. And www.example.com automatically follows because it just points to the name.
Ah, clever. Keeps things tidier. Okay. And MX records. I'm guessing M for mail.
Spot on. MX stands for Mail Exchanger. MX records tell the internet which servers are responsible for handling email for your domain. When someone sends an email to you at example.com, the sender's mail server does an MX lookup for example.com to find out where to deliver the message.
So DNS isn't just for websites, it's directing email traffic too. Like the post office knowing which mailbox belongs to which address.
Exactly. Absolutely crucial for email.
Okay. What about TXT records? Text. What's that used for?
TXT records are kind of a general purpose record. They let you associate arbitrary text strings with your domain. Really common use is for verification.
Verification. How?
Like if you sign up for Google Workspace or Microsoft 365, they might ask you to add a specific unique TXT record to your domain's DNS settings. This proves to them that you actually control the domain.
Ah, okay. Like putting a secret code in your public listing to prove it's yours.
Kind of, yeah. They're also used for important email security stuff. Things like SPF, DKIM, and DMARC rely on information stored in TXT records to help prevent spam and email spoofing. Think of them as little notes or metadata attached to your domain.
Interesting. Versatile. Okay, and NS records. Name server. That sounds like it points to the servers themselves.
Precisely. NS records delegate authority. They specify which authoritative name servers are responsible for a particular domain or subdomain. So the TLD servers use NS records to point to the authoritative servers for example.com. And if you had subdomain.example.com, you could use NS records to delegate control of that subdomain to different servers.
Okay, so they define who's in charge of the records for a specific zone.
Yeah.
And PTR records. That was described as a reverse lookup.
Exactly right. PTR is for pointer records. It's the opposite of an A or AAA record. Instead of name any IP, it's IP name.
Why would you need that?
It's often used for security checks and logging. For instance, an email server receiving mail might do a reverse lookup on the sending server's IP address to see if it matches the domain name it claims to be sending from. Helps fight spam. It's like having the phone number and wanting to find the name associated with it.
Got it. Reverse phone book lookup.
Yeah.
And the glossary also briefly mentioned things like SRV, SPF, DKIM, DRArch. We don't need a deep dive on each, but it highlights that DNS holds more than just web addresses.
Absolutely. SRV records help locate specific services like voice chat or instant messaging running on a domain. And yeah, SPF, DKIM, DRG are all critical for email authentication today. It shows how adaptable DNS is. It stores all sorts of crucial operational data for the internet.
It's clearly fundamental. Okay, so why should the average listener care about all this DNS stuff? What are the really practical applications we experience every day?
Well, the absolute biggest one is just web browsing, like we said at the start. Every single time you type an address, click a link, load an image on a page, DNS is working silently in the background.
Without it, we'd need to memorize those strings of numbers.
Yeah, forget it. The internet wouldn't be usable in the way we know it. So basic web navigation totally relies on it.
Okay, that's huge. What else?
Email delivery. Completely dependent on DNS, specifically those MX records we talked about. You send an email, the system needs DNS to find the right destination server. No DNS, no email. Simple as that.
Wow. Okay, browsing and email, that covers a lot of online activity already.
Yeah.
What about load balancing? Our source mesh and big websites use DNS for that. How?
Right. So very popular websites, they can't just run on a single server. They'd get overwhelmed. They often have many servers, sometimes spread out geographically.
Makes sense.
DNS can be set up to help distribute the traffic. When you ask for the IP address of, say, a huge news site, the DNS server might give slightly different answers to different people or rotate through a list of server IPs.
So it spreads the visitors out across multiple servers.
Exactly. It helps prevent any one server from getting overloaded and keeps the site responsive for everyone. It's like a big store having multiple checkouts open instead of just one.
Clever. Using DNS to manage traffic flow. What about security? How does DNS play a role there?
DNS can be a first line of defense. Many security services and some public DNS resolvers maintain block lists of known malicious domains, phishing sites, malware distributors, etc.
Okay.
If you try to go to one of those bad sites, a security-focused DNS server can simply refuse to resolve the address or redirect you to a warning page. It stops you before you even connect to the dangerous server.
Like an internet bouncer checking IDs at the door.
Kinda, yeah. It helps block threats at a very early stage.
Cool. And the last one mentioned was CDN's content delivery networks. How does DNS help make websites load faster with those?
Okay, so CDNs work by storing copies of website content, like images, videos, code, on servers all around the world, much closer to the end users.
Right, so the data doesn't have to travel as far.
Exactly, and DNS is key to making this work. When you request content from a site using a CDN, the CDN's DNS system looks at where your request is coming from geographically, and it gives you the IP address of the CDN server that's closest to you. So you get the content from nearby, making the website load much, much faster.
Ah, so DNS directs you to the nearest copy.
Very smart.
Okay, so DNS isn't just finding the address. It's critical for speed, reliability, security, load balancing, email.
Well, it really underpins a lot.
So let's talk about the companies involved. Who are the players in this DNS world? Our source material outlines several types of vendors and providers.
Yeah, it's quite an ecosystem. First up, you have the DNS registrars. These are the companies where you actually go to buy and register your domain name.
Like GoDaddy, Namecheap.
Exactly. GoDaddy, Namecheap, Google Domains, which is now part of Squarespace. Actually, Cloudflare has a registrar service too. Domain.com, lots of them. They're like the official land registry for internet domain names. You pay them to reserve mycoolsite.com.
Okay, so they handle the ownership part.
Yeah.
Then there are managed DNS providers. What's their deal?
These companies run the actual high-performance DNS infrastructure, the authoritative name servers we talked about. They focus on providing super reliable, fast, globally distributed DNS hosting.
So if I have a business website, I might pay one of these companies to handle the DNS lookups for my domain.
Precisely. You'd point your domain's NS records, which you configure via your registrar, to their servers. Big names here include Cloudflare, Amazon Route 53, Google Cloud DNS, Akamai, NS1. They handle the heavy lifting of answering queries quickly and reliably worldwide.
Right, the infrastructure operators. And DNS security providers, separate from managed providers.
Often they overlap, but some companies specialize in security. They offer DNS services specifically designed to filter out malicious sites, prevent certain types of attacks like DNS poisoning, and often add privacy features.
Examples.
Cisco Umbrella, which used to be OpenDNS, is a big one, especially for businesses. Cloudflare's 1.1.1.1 public resolver has strong security and privacy aspects. Quad9 is another public resolver focused purely on blocking malicious domains. They're like the security specialists for your DNS lookups.
Got it. And we mentioned CDNs often have DNS features too.
Yeah, absolutely. Companies like Cloudflare and Akamai are huge CDNs, but they also offer very sophisticated DNS services. It makes sense because, as we discussed, DNS is crucial for directing users to the right CDN edge server, so they integrate it tightly.
Makes sense. Okay, what about public DNS resolvers? We've mentioned a couple.
Right. These are alternatives to just using whatever DNS server your ISP automatically assigns you. Anyone can typically use them for free.
Why would I switch?
Often, they can be faster than your ISP's default servers. Sometimes they offer better privacy policies, not logging your queries as much. And some, like Quad9 or Cloudflare secured options, provide that malware filtering we talked about.
So famous examples are
Google Public DNS, which is 8.8.8.8 and 8.8.4.4. Cloudflare's is 1.1.1.1 and 1.0.1, 1.0.1, 1.0.1. Quad9 is 9.9.9.9. They're easy to remember and popular alternatives.
Okay. And the sources even mentioned DNS software providers and analytics monitoring companies. It's a whole industry.
It really is. From the core software running the servers, like BND or not DNS, to tools that analyze DNS traffic for performance or security issues, there's a lot going on to keep this global system running.
Wow. Okay, so it's a complex ecosystem. But like any big system, things can go wrong, right? Our source touched on some common DNS problems and solutions. DNS propagation delay was one we mentioned, that waiting time.
Yeah, that delay when you update a record, it can be frustrating. It's not really a problem in the sense of something being broken. It's just the nature of distributed systems, but it means users might see the old website or service for, minutes or even hours after a change. You just have to plan for it.
Right, the waiting game. But then there's DNS poisoning.
Yeah.
That sounds actively bad.
It is. DNS poisoning, or DNS cache poisoning, is a real attack. Malicious actors try to trick DNS resolvers into caching incorrect information by sending forged responses to the resolver's queries. If successful, anyone using that compromised resolver could be sent to a fake website, like a fake bank login page, even if they typed the correct domain name.
Yikes. That's like someone sneaking a fake entry into the phone book. How do we stop that?
The main defense is DNSAC, DNS security extensions.
DNSSEC. Okay.
DNSSEC uses digital signatures to verify DNS data. The authoritative server signs its records with a private key. Resolvers that support DNSSEC can then use the corresponding public key to check that signature.
So it proves the data came from the legitimate source and wasn't altered.
Exactly. It provides data integrity and origin authentication for DNS responses. Think of it as a tamper-proof seal on the information. Adoption isn't universal yet, but it's growing and it's crucial.
Okay, so DNSAC helps fight poisoning. What about other issues? The source mentioned DNS failover.
Yeah, that's about reliability. If your primary authoritative DNS server goes down, DNS failover systems can automatically reroute DNS queries to a secondary backup server. Ensures your website or service stays reachable even if one server fails.
Good redundancy. And split horizon DNS sounds intriguing.
That's often used in corporate networks. It means configuring your DNS server to give different answers for the same query depending on who is asking specifically, whether the request comes from inside the internal network or outside on the public internet.
Why?
So internal users might get an internal IP address for a company's server, while external users get the public IP address. Useful for managing access and security.
Okay. And briefly, DNS leak and DNS sinkhole.
A DNS leak is mostly a privacy concern, especially with VPNs. It's when your DNS queries accidentally bypass the secure VPN tunnel and go out via your regular ISP, potentially revealing your browsing activity.
Ah, okay. And a sinkhole.
A DNS sinkhole is a security technique. You deliberately configure a DNS server to give a false controlled IP address for known malicious domains. Any traffic trying to reach those bad domains gets redirected to this sinkhole server, where it can be logged and analyzed instead of reaching the actual malicious site.
Using DNS to trap bad traffic. Clever. It's clear a lot goes into keeping DNS running smoothly and securely.
Definitely. Constant effort and evolution.
Finally, our deep dive touched on some advanced concepts, peeking behind the curtain a bit more. Anycast, DNS was one.
Anycast is very cool. It's a networking technique where you announce the same IP address from multiple geographical locations.
Same address, different places. How does that work?
The internet's routing protocols automatically direct a user's request to the nearest location advertising that IP address. Many large DNS providers, CDNs, and root servers use Anycast. Two big reasons: speed. Users connect to a server close to them, and resilience. If one location goes down, traffic automatically reroutes to the next closest. Think of it like a big chain store, same name, IP address everywhere. You just go to the closest branch.
Super efficient. Okay. And DNS load balancing, we touched on it, but are there fancier ways?
Yes. Basic load balancing might just rotate IPs. That's often called round-robin DNS. More advanced methods can factor in server health. Is the server responding quickly? Current load, or even the user's geographic location, GeoDNS, to make smarter decisions about which IP address to return. It's like a really intelligent traffic cop.
Got it. And then DNS over HTTPS, DOH, and DNS over TLS, DOT. These sounded like privacy boosters.
Exactly. Traditionally, DNS queries were sent unencrypted, in plain text. Anyone snooping on the network path could see which websites you were looking up.
Not great for privacy.
Not at all. DOH and DOT both encrypt your DNS queries between your device and the DNS resolver. DOT wraps them inside standard HTTPS traffic, like secure web browsing, while DOT uses TLS encryption on the standard DNS port.
So it hides the lookups.
Essentially, yes. It makes it much harder for third parties on the network, like your ISP or someone on the same public Wi-Fi, to see your DNS activity. It's like having your DNS conversation in a soundproof room, DOT, or sending it in a sealed, opaque envelope, DOH.
Important for privacy. And the source just listed a few others: round robin, wildcard DNS, reverse DNS, which we covered, eDNS, GeoDNS. Seems the rabbit hole goes deeper.
Oh, absolutely. Wildcard records let you define a record for any subdomain that doesn't have a specific record. eDNS allows extensions to the original DNS protocol for new features. GeoDNS, as mentioned, directs users based on location. DNS is surprisingly sophisticated under the hood.
Wow, okay. So wrapping this up, DNS is clearly way more than just that simple phone book analogy we started with.
Definitely. It's a foundational, distributed, hierarchical database system that's critical for translating names we use into addresses computers need. But it also handles email routing, service discovery, load balancing, security filtering, CDN direction.
And it has layers of security like DNS SEC and privacy enhancements like DH and DOT. It's this invisible but absolutely vital engine making the internet work for us.
That's the core takeaway. Seemingly invisible, but utterly crucial.
And it's really amazing when you think about all the parts, the different server types, the record types, the whole resolution process, the companies involved.
Yeah.
All working together globally.
Which brings us to maybe a final thought for you, our listener. The next time you type a website address, just take a second to appreciate that you're kicking off this incredibly complex worldwide lookup that usually completes in milliseconds.
Yeah, it connects you almost instantly.
So consider, what other unseen systems are powering our digital lives in such profound ways? And maybe more starkly, what would actually happen if DNS just stopped working tomorrow?
That is a truly thought-provoking question, definitely something to mull over. If you're intrigued and want to dig deeper, maybe check your own computer or phone's DNS settings sometime, see what servers you're using, or look up some of those providers we mentioned, like Cloudflare or Quad9.
Yeah, there's always more to learn about this foundational piece of the internet.